It's one of the largest ones in the world, and the largest one focused specifically on automation. There's a lot of other companies that do this, but Rockwell's the largest that does only this. My background is I've done a whole lot of different things. I started out with a degree in electrical engineering and then went and did like web application type development for a few years. While I was doing that, I did some work on hardware security, so that's real low level. Then I did a lot of data processing type work, and then went to go work on security for embedded in industrial control systems. So I guess I'll give you a little overview of what this whole presentation is going to be. So introduction, just got that over with. Then I'm going to talk a little bit about industrial components and PLCs. How many of you know what a PLC is? Okay, that's good. So about 30–40%. How many of you have actually used one? 1 2/2. Okay, good. So we've got one here. You guys will be able to come up and poke at it and take a look at it at the end of this presentation. So we'll talk about that along with some of the other special pieces that go into industrial control systems. I'll go over a little bit of the history of industrial control system security. So specifically two major events. One of them was about, I guess, 3 major events. One of them was not an attack, but was actually a research project. And then 2 different attacks, one of which was about 10 years ago, and the other was about a year and a half ago, maybe 2 years ago. And then I'll talk a little bit about some of the issues that come up in industrial control system security that don't really come up in most of the other security that exists out in the field of cybersecurity. All right, so I talked a little bit about who I am. So Rockwell, the company I work for, it's about a $7 billion company with about 23,000 employees in most countries. So let's get on to the actual technical stuff. So industrial components and PLCs. So what is a PLC? A couple of you guys said you were aware of what they are. 1 or 2 of you said that you've actually used one before. So these are PLCs. Specifically, these bottom 2 devices, and then the devices. So what actually is it? A PLC stands for Programmable Logic Controller. I think I've actually got it too. It's essentially a special purpose computer built for industrial environments. A lot of people will say, and I've had people actually running plants ask this, go on it. I can load my own custom programs onto it. It's not more of a proprietary system. These are some of the reasons that you'd actually do that. So one of the main reasons is there's a lot of real-time constraints that go into PLCs. So if you're controlling a system that has either safety aspects to it, so if somebody could get injured if timing's not accurate, or potential environmental damage, so things like nuclear reactors, power plants, chemical facilities, all of those have lots of PLCs in them. You don't want those to go wrong, and you want to make sure that when it says it's going to do some operation in a specific amount of time, that it actually is guaranteed to do that. And the other major reason is environment. So if you get a Raspberry Pi, it'll work great on your desktop. It will not work well in extreme temperature ranges. So some of these values up here are for some of our environmental hardened controllers, which this is not, but it's actually pretty close to these specs as well. So minus 25 to 70 degrees C. So it could be mounted up in the Arctic somewhere, or it could be mounted next to a steel furnace. Some of these devices are in places where people can't actually get to them. They get put in when a system's installed, and then they're left alone because the environment's too hazardous to actually go near it. Shock resistance. A Raspberry Pi works great if it's not moving. If you run into it with a forklift, it's probably going to stop working. The PLCs are generally rated into the 30 to 50 G shock rating, and they're also vibration tested too. So if you have an environment like an engine for a ship, there's a lot of vibration on there that over time would wear out the solder joints on something like a Raspberry Pi or even a desktop computer. So these are built to actually withstand those environments. Again, along with the idea of something like a ship engine, it's not exactly a great environment for computers. So there's a lot of humidity. If you're out on the ocean, there's a lot of salt, which corrodes electronics really, really quickly. There's a lot of, and one of the main ingredients is chlorine. If you're working around that, it will eat away at your computer pretty quickly. And you can also have surprise sparks that are then going to make your plant turn into a large crater, which does occasionally happen, and there's a lot of effort that goes into making sure that doesn't happen. The other aspect of PLCs is they're designed for a really long lifetime. With standard sort of IT assets, they generally get replaced every 3 to 5 years. So if you've got a 6-year-old laptop, it's probably pretty slow and doesn't work the way it did when you got it, and probably does all sorts of funny things you don't expect it to. That's not very long for PLC. There are a lot of PLCs out in the world right now that were built in the 80s and are still running because you put them in, your system works, and you don't want to turn it off. And in some cases, you can't. The example that we use pretty often, we actually had to give this example to Microsoft when they were doing a threat modeling training with us around why we some of the updates and patches is glass manufacturing. So when equipment to actually turn that glass into whatever shape it's going to be. The problem is, if it cools off, it turns into solid glass and does not melt very easily again. So if you turn off a glass factory, it's done. You have to start running bulldozers and build a new one. So 30 to 50 year life expectancy is not uncommon. And they need to be reliable enough that it's not going to decide, I'm going to reboot right in the middle of you working on a project that needs to get done in the next few hours, as I'm sure a lot of you have experienced. So it needs to turn on, stay on, and continue running flawlessly for potentially decades. The other unique aspect of PLCs is they don't usually use the same type of languages that you guys would be used to. What languages do you guys generally do stuff in? I'm guessing C, C++, Java, Python. Okay. So PLCs generally use a language called ladder logic. It's more of a pictorial graph representation of logic. That was done because PLCs were originally built to replace actual relay systems. So in a really old plant, and actually a lot of them still today have these around because if they work, you don't want to pull it out and potentially shut down your glass factory. They would have these big boards where they'd have physical relays all wired together, and they would physically implement the logic to run a machine, a plant, something like that. When PLCs first came out, the people who were programming these were the same people who maintained these giant systems of relays. And so that's what they were used to looking at, is the diagrams of here's how the logic should be built physically into these relays. And so the programming language was actually built to mimic that. And we'll look at that a bit later and actually take a look at what some of it looks like when we work on this traffic light. There are actual languages that do look like text. There's one called structured text that's more common in Europe and is becoming more common just because the general age of people who are working on them are people who are used to C and C++ and Python and those type of languages. But there is also languages that are more system-oriented. How many of you guys have taken like a systems and control class? Okay. So have you done like PNID?
I don't know if we ever went over that, but
okay.
It was just control systems, you know, signals and systems, kind of continuing along that lines.
Okay. Have any of you guys done like PID control or any of that type of stuff? Okay, so you're at least familiar with it. Essentially, these are mathematical algorithms that take some set of inputs and use it to drive some process at the other end. And writing all of that logic is not something that somebody would really like to do over and over again. So PLCs generally will have the ability to say, here's a block that contains all of that logic. I can put my parameters into it, and then I can hook up my inputs and hook up my outputs, and that's all the programming you need to do. All right, so what are PLCs? So this is a pickle machine. This big gray box in the back that's got a bunch of big buttons and switches on it, that's where PLCs generally live. So anytime you go into a factory and you see those big gray cabinets, they're the computers inside that are controlling the actual process. So here, this would be conveyor belts, temperatures, agitators, stuff that moves, and any sort of sensors to tell you you're making pickles the right way, or maybe you're doing it the wrong way. So automotive plants. Automotive plants are full of PLCs. So all of these robotic arms, they're all controlled by PLCs. Most of them have, most of the PLCs have specific commands for doing things like motion planning. So how do you make a robotic arm go from here to over here without hitting a bunch of stuff in the way? All of that logic's sort of pre-built in, where you can say, here's an environment and it can move from here to here. Beer. Most breweries have at least a couple different PLCs in them. So they're used for things like moving grain back and forth, moving fluids, temperature control, process monitoring. They're used for carbonation. A lot of breweries will use forced carbonation, where they have a chilled liquid pumped through a high pressure carbon dioxide gas. And that's a very delicate process that you have to get right. Otherwise, you get bottles that explode when they have too much CO2 in them. Wind turbines and energy generation. Just about every wind turbine has at least one, usually a couple different PLCs in them, and they'll do things like adjust blade pitch. So how do you get the maximum amount of energy out of a wind turbine? You need to make sure it's facing the right way. You need to make sure that your blades are angled the correct direction. There's gearboxes inside of them that are electronically controlled to optimize power output. And they also do things like, if you're somewhere that gets tornadoes and one's coming through, it will lock those blades in place so that they don't spin faster than they're rated to. Because each one of those blades has a stress rating, and if you exceed that, then your entire windmill blows up, and that's bad. So package handling. Places like USPS and UPS and FedEx have enormous warehouses. Some of them are several square miles that have these giant conveyor belts that scan package labels and weigh them and try and optimize how they fit into different trucks. All of these conveyor systems are controlled by PLCs. So they'll hook up to barcode scanners or optical scanners, so cameras that can do some additional processing, and they'll say, here's a box, it needs to end up at this location, here's a truck that's going to this location, it's over on the other side of this factory, here's how I move a bunch of different conveyor belts to get it there. Baggage handling system. So if you go to an airport and you wonder why your luggage is taking forever to actually show up when you landed an hour ago, it's because it's going through a giant system very similar to what the shipping facilities have, where it takes it off of a tarmac and then moves it through an airport to the baggage carousels where you can actually pick it up. And you can see again, here's these big gray cabinets that have the actual control hardware inside of them. This picture is actually interesting too, because over here, right in the middle, you can see a big sensor array as well. Yes?
Are they the reason we lose all our luggage?
Potentially. So one of the issues with a lot of systems like this is they're mechanical, and anytime you have something mechanical, you have the possibility of stuff just getting stuck or stuff falling off of conveyor belts. So a PLC can say this needs to go from here to here, but you actually need the instrumentation to make sure that I told it to go from here to here, did it actually get there? If not, where did it go? There's different ways that you can do that. Sometimes you can just put in a whole bunch of sensors, but it's usually cheaper to do something like RFID tag items. I don't know that any airports are doing that. I do know a lot of logistics companies are. So something like Apple wants to ship a computer somewhere. They want to know that it got onto a truck, and they want to know that it got off at the right place, and that it got into the right storeroom, and that it got handed to the right person. Things like that, they'll tag with an RFID tag. And at each one of those points, they can have an automatic scanner that goes through and says, here's all of the RFID tags that I'm picking up on this lot of items. And that can feed into either PLCs or a lot of the network infrastructure that sits above them to do that control and monitoring. That answer your question? Traffic tunnels, and this applies to train tunnels as well. One of the sort of unusual applications for these is ventilation systems in tunnels. And these are usually redundant systems as well. So they'll build the entire system twice and then have it physically separated somehow. And the reason they do that is if you have a traffic tunnel, there's a lot of cars going through it, and cars produce carbon monoxide and all sorts of other stuff you really don't want to breathe in, especially when you're in a several mile long space. So they'll put these redundant systems in place so that if something goes wrong with their air handling system, it'll automatically hand it off to another duplicate system and then alert somebody that, hey, something's not doing what it's supposed to prevent things like people getting poisoned by driving through a tunnel. Does anybody know what this is? Almost. So this is a liquid natural gas tanker. So the great big round balls on the top of this ship are actually big spherical chambers that when they dock in port, they pump pressurized natural gas into these big tanks. And then they ship it across the ocean. So this is how natural gas actually gets transported around. It's inside of one of these giant ships. Each one of these containers is going to have equipment for monitoring for leaks, because leaking natural gas is bad. They're going to have additional controls to make sure that nobody's opening the connections to this. If you've got a big hatch into one of these natural gas tanks, you really don't want to open that because it's under a lot of pressure and it's under a lot of pressure from an explosive gas. So there's a lot of safety systems that go into making sure that once you put it in, it stays where it's supposed to and it doesn't do anything it's not supposed to. Also, along the back of this, you can see there's another one of these arrows at the very back of the ship where there's not one of these tanks. I had said before, a pretty common application is things like marine propulsion. So ship engines will use PLCs to either control the engines that are driving them. A lot of ships will use a hybrid system, so they'll have an electric motor that's run off of a gas generator similar to a hybrid car. So there's a lot of power transmission and motor control that goes into that. So that's another pretty common application. Oil platforms. There's a ton of stuff that can go wrong on an oil platform, and if something goes wrong on an oil platform, you're stuck on that oil platform with whatever went wrong. So there is a lot of safety systems that go into oil platforms. That includes things like pressure monitoring, temperature monitoring. I had mentioned before about explosive atmospheres. If you're working right next to a drilling head on an oil platform, there's potentially all sorts of explosive gases coming out of that. You don't want to be using a Raspberry Pi that when you pull a wire out of it, it creates a spark and now your oil platform's on fire. So there's generally several hundred PLCs in an oil platform like this. Transportation, so things like trains. If any of you guys have been to an airport that's got one of these trains, this is the one at the Orlando airport. These are entirely controlled by PLCs. So there's generally a couple of them actually built into the train, and there's usually a couple of them built into the tracks. So the train can move itself automatically, and the tracks can keep track of where the train actually is. So generally you'll notice there's nobody actually driving them. You just sort of get on and then it takes you off to wherever its next stop is. All of that is done by PLCs. Entertainment, so things like roller coasters. Roller coasters have a lot of moving parts that you want to make sure that they all work correctly, especially when you're strapped into one. So the motors that drive them, a lot of roller coasters now are using electromagnetic accelerators. So it's basically a big electromagnet that just sort of yanks the thing forward. All of those are controlled by PLCs. The brakes to make sure that you actually stop and don't hit the car in front of you when you come to the end of the ride is there. And also for just general comfort while riding these things. If something goes wrong and it decides it's going to just try and accelerate as fast as it can for as long as it can, that's generally not a good thing. Some of these are built in such a way that without that control, it could potentially injure someone. So again, this is another place where those safety systems come into play that make sure that when it says stop, it actually stops rather than continuing on to run into something or exert more G-forces on somebody than they would like. And a lot of chemical processing. So just about every chemical has some complicated process that goes through one of these giant plants like this to come out with whatever your end product is. The pressures and temperatures and the different stages of those processes are all controlled by PLCs. And again, there's a lot of those safety systems similar to like an oil platform, just to make sure that if something goes wrong, it can be monitored and stopped before it becomes a real issue. So that's sort of where PLCs are and what they do. But I also wanted to touch briefly on a couple other pieces of industrial control systems just because they do affect the security of these systems as well. So the first one is SCADA systems. So SCADA stands for Supervisory Control and Data Acquisition. This is when you see these big control rooms like this. I believe this one's from a power plant. That's a SCADA system. Essentially what it says is I've got a PLC here and another one over there and another one over there, and then I've got all of that feeding up to some cloud server somewhere to aggregate data. This is the thing that puts all of that together. So it will centralize some of that data. It'll show information on the different processes that are running. It will show error states. So one of the things that PLCs do really well is they can be set up to identify errors and then handle them in a way that people can address them appropriately. With general software, if you get an error, your program either says, here's some logic to handle it, or it crashes. With a PLC, you really don't want that to happen, so you can tell it, hey, if you crash, dump what you're doing, reload what you're supposed to be doing, and then tell somebody, hey, something went horribly wrong, go figure that out when you get a chance. So that type of information will all be centralized in a system like this. HMIs, so these all look like old computer screens from the 90s. But what these are is they're actually industrial touchscreens. So very similar to PLCs with the environments. If you wanted to have an interface on a machine somewhere in a plant that may not be in the ideal environment for a touchscreen, you can use one of these. So again, they're rated for several hundred degrees and humid environments and explosive atmospheres and all of those same type of things. And what these do is these act as a more advanced interface to a process or a system or a machine than some of the older systems, which are a big panel full of buttons. So in the past, you'd go up, you'd want your machine to start, so you'd go and you'd push the green button that says start, and then when something went wrong, you'd push the red button that says stop. And that was the extent of your control. With HMIs, you can do all of that. You can actually see down here, these look like those little buttons that used to be on the big metal panels, and a lot of them still do have those panels as well. But you can also get a lot of actual process information. So what is the temperature of my batch of product that I'm making? Or what is the success rate of producing a device that I'm making? So if I'm making 1,000 pieces and 500 of them are bad, I can monitor that and show that information on an HMI so that the technicians actually working in these plants can look at it and say, well, that shouldn't be happening, that's way out of normal, let's take a look at what's actually causing it. This should have had a picture in it. So there's a whole series of sensors and actuators that go along with this. They're everything from temperature probes to pressure monitoring to vibration monitors. Float switches are pretty common, so kind of like the thing in your toilet when it fills up and it stops running. Those type of switches are really common in industrial processes. And each one of those sensors and actuators has their own set of communications and communications protocols that they use. So some of them use things that you guys are probably very familiar with. So sort of TCP/IP or Bluetooth or Wi-Fi, things like that. A lot of them use other protocols that you guys probably have not come across. So things like DeviceNet or Modbus that are very purpose-built for these industrial systems. And a lot of them were purpose-built back in the 80s when you didn't really have a lot of bandwidth to work with and you didn't have things like switch networks. So a lot of them are designed for hardwired sort of control bus type systems. All right, so that's sort of the devices and what they do and where they're used. Does anybody have any questions on that? No? Cool. All right, so history of ICS security. So there's a few different things I want to talk about in this. There's a lot of history here, but there's a few main areas I wanted to talk about. So the first one is the Aurora generator test. So this is really the first time that somebody got one of these devices and said, hey, I wonder if I can hook it up to a network and do bad things with it. So this was a test that was done at Idaho National Labs. They're a government research lab out in Idaho Falls in Iowa, or in Idaho, that does research on nuclear reactors and control system security. So those are sort of the two main focuses that this lab has. And as part of that research into control system security, they did this test back in 2007 and released a little bit of information about it then. But I'll let you guys go ahead and watch this video of this test, and then I'll explain a little bit about what it's actually doing and why it's doing the things it does. So here you can see this is a motor control system. So it basically handles power distribution. This is a large-scale electric generator. So this would be something like a power grid would have for generating power. And you can see it vibrating in ways that don't look like what it should be doing. In a minute, you can see it actually failing.
Oh.
All right, so that was the Aurora generator test. So what they did is this was done entirely by just sending commands over a network. They figured out the right way to time these commands and the right sequence of commands to send to actually blow up that generator like that. So most of the information about this test, yes?
How much does that generator cost?
Probably $500,000. Yeah, they're not cheap. There are cases where much more expensive pieces of equipment have been damaged in very similar things like this. I can talk about some of those. Those are probably in addition to the items that are in here. So when this was originally done, INL released a statement saying, hey, we did this thing, it's possible to do, here's a little bit of information about it. And then they sort of didn't say anything else. And that was the case until 2004. When somebody submitted a Freedom of Information Act request for a different thing also named Aurora, which was a Chinese state-sponsored attack on several companies in California. So it was essentially a distributed denial of service against things like Google and Yahoo and Rackspace and potentially a bunch of other companies. And because of a string that was in the path that was used for the executable to do this, they named it Aurora because that was the name in there. Somebody submitted a request saying, hey, I want all of the information on this Aurora attack that you guys have. And the person at the department responsible for responding to those requests said, this says Aurora, so I'm going to send it out, despite it being completely unrelated. So all of the information about this is now publicly released because somebody accidentally released something with the same name. All right, so what did they actually do? So this is a protective relay. These are devices that are in a lot of high power systems. So when you start getting things like power substations or switching substations or power generation facilities, they'll have these big relays and they're about this big. Some of them are even larger, depending on what type of power they're handling. So these devices are designed to protect that hardware from exactly this type of thing. Because occasionally something will happen in the system that it will need to disconnect to protect that hardware. And it'll say, I would rather turn off the power than blow up my $500,000 machine. The thing that the guys at INL found out is, well, we've got about 15 cycles or so of this machine running in a circle. So it's a big motor. How many of you guys are familiar with how motors work and the electromagnetics of it? Okay. So in a motor, you've got a great big magnet. It spins around. You've got coils of wire, and because that magnet's going past those coils of wire, it creates electrical flux. And that is what actually pushes the power around and out of these motors. Well, what these guys found out is when we turn off these protective relays, we've got a few parts of a second where we can turn them back on. And if that generator is not spinning exactly in phase with the electricity that's on that grid, it can go until it's about 180 degrees out of phase. So some of you guys were talking about some of your circuit stuff. If you guys have done anything with AC yet, you started to do phase diagrams and all of that fun stuff. When you've got a magnet that's out of phase with the power it's trying to keep up with, it tries to line itself up really, really fast. And when it can't physically line itself up fast enough and it weighs a whole lot, all of that power has to go somewhere. And that somewhere is the rest of that machine. So if we go back up here, go to that here. Each one of those times where that machine sort of jumps up and down, they're sending a command to say, disable that protective relay, let it run freely for a few seconds till it's out of phase, and then close it again so that it tries to snap back into place where it's not designed to do. And if you do that enough times, you eventually break something important and you get this. Jeez. All right, so that's the Aurora generator test. That happened. The news sort of said, the government did this interesting thing, and that was about it for quite a while. The next thing that happened, oh, here we go. Yeah, so minus generator, disable the rotor till it's out of phase, re-engage it, and it'll try and match. The next thing that happened was at this plant here. So this is the Natanz nuclear facility in Iran. How many of you guys know about this at all? Okay, so most of you. So you guys are probably familiar with Stuxnet and how it works. I guess maybe not how it works, but at least that it happened and it damages nuclear centrifuges. That's generally what people know about Stuxnet in general. So I'm going to talk a little bit more about how it actually works and why it does some of the things that it does. So this is actually a picture from inside of the plant. These big silver columns here are the nuclear centrifuges. So what they do is they'll take uranium hexafluoride and they will spin it around until it condenses out uranium. But that's a very delicate process because uranium's heavy and it breaks things pretty easily. And the way that Iran decided that they were going to build this system so that it would continue working is they were using these IR1 centrifuges, which were late 60s, early 70s design that they had sort of bought on the black market and said, okay, we've got this component, we need to put it together and make something that we can actually refine uranium out of. The problem is these centrifuges are really, really fragile. And if you use them wrong, then the uranium hexafluoride condenses into a solid, and it breaks your centrifuge. And one of the difficulties of using these centrifuges is the higher the pressure that you have in these centrifuges, the more efficient they are, but also the easier it is for them to break. So the approach that Aurora took is, you can see here, there's 2, and then there's another row back here that's got 3, and then several more with 3. They essentially took a redundancy approach, where they had several of them running in parallel, and if one of them went wrong, they would just shut that one off, and they'd leave the rest of this big cascade of centrifuges running. So it would pump raw material into the middle of this big cascade. It would refine the uranium hexafluoride in one direction, and it would refine out everything else in the other. And as centrifuges failed, they figured we can make them faster and cheaper than actually fix them. So we're just going to make a whole bunch of them, and when they die, we'll go make more. So how did this actually work? So this facility was a completely air-gapped facility. So no network connections, no interface to the outside world. You wouldn't be able to find it on the internet. So it got into that facility through a contractor's laptop. So somebody, the currently suspected parties involved, or the US and Israeli governments, went around and dropped a bunch of flash drives in a parking lot somewhere where they knew that contractors from this facility would be. And one of those contractors picked up one of those flash drives, stuck it into his computer that he was then going to take into a secure nuclear facility, and then hooked it up to that network. So that's why you don't plug in flash drives. So what was actually on that flash drive was a really interesting piece of software. You can actually find it on GitHub now, I believe, for a couple different reasons. So one is it looked for specifically the type of control system that was used in these centrifuges. Iran was using a Siemens Step 7 process controller because they were cheap and they could find those pretty easily on the black market. So it would go and look at a device and say, is this the specific controller that I'm looking for? If not, then it would not do anything. It would just sort of go quiet. If it did find one of these controllers, it would say, okay, great, this is the right device. Is it connected to the right kind of equipment? So it would go out, it would check, make sure it's connected to one of these centrifuges. And then once it said, yes, I'm actually connected to a nuclear centrifuge and doing the right process that I want to mess with, it would install itself on the PLC, and then it would wait. So what it would do is, once it was installed, it would every once in a while wake up, and it would modify the rotor speeds. So the nuclear centrifuges, I want to say they run at about 60 cycles a second. It would very quickly speed them up to about 120, down to about 3, and then back up to 60 or so. And it would just do this every once in a while. While it was doing this, it would tell the PLC, hey, I'm not really doing this. So we talked about the SCADA systems and HMIs a little bit ago. Normally, if you've got a PLC that's doing something funny like that, it's going to show up on either your HMI or in your SCADA system, where you can see, hey, I'm getting these weird velocity spikes, it shouldn't be doing that, we need to go and take a look at why the control is telling it to do that. Part of what was actually in the Stuxnet worm was code to overwrite the outputs, where it would record for a little while. So it would say, here's what this specific centrifuge is doing over a couple hours. It would pick about 10 minutes of that out. And then as soon as it started modifying that rotor speed, it would play back that information. So it would dynamically sort of copy data out of one of these systems so that it could tell the system's monitoring that, hey, everything's all right, you don't need to worry about anything. The other piece of this that's really interesting is some of the ways that it actually got into the systems. Generally, when you have something like a virus, there are a lot of programs that look for common things and programs. I'm sure you guys have seen a lot of the antivirus type software or some of the more dynamic firewalls that actually check contents of data. The way that Stuxnet got around that is it actually had a signed executable. Actually had two. There were two companies in Taiwan that had drivers for things like keyboards and mice and printers and common things that you'd find connected to a PC. And the Stuxnet virus was actually signed with a valid certificate saying, basically, this is a keyboard. So somebody plugs in their computer, this program gets loaded onto it, Windows looks at it and says, oh, this is a keyboard, I should let that in. And then it goes and it starts trying to install itself on PLCs to damage centrifuges. Another interesting piece of this is it was not designed to cause an immediate failure. The velocity spikes wouldn't break a centrifuge, but what they do is they would drastically shorten the lifespan. So you wouldn't have a single event where you could say, here's something went wrong, my machine broke, I need to look into exactly what it was doing in right about this very short time frame. It would slowly, over the course of a couple weeks, speed up and slow down these rotors so that it would damage the centrifuges, they'd get less reliable, and ultimately it increased the failure rate by something like 50%. So if you can make a lot of these, then you can keep replacing them, but if you need to make a whole lot more, it starts to get much more difficult. The way that Stuxnet was actually detected eventually is it, despite being in an air-gapped network, had a command and control server mechanism for updating. So it would try and find ways out to the internet. Again, using several different 0 days. There were, I think, 4 of them in there. It would go out onto the internet, it would look for some of these command and control servers, and it would slightly change how it operated. So there's actually several different variants of Stuxnet out in the world that you can find. Some of them still show up on devices. And it started out being incredibly stealthy and only looking for these one specific type of controller connected to this one specific type of centrifuge. And as time went on, they sort of got more aggressive in the things that they would attack. And there's a lot of speculation about why it did that. Some people said basically somebody wanted this to be found so that people would go, hey, we need to actually do some of this security on industrial control systems. And some of it is it did what they needed to, and so then they decided to see, okay, what's their detection capability? If we start making this more and more obvious, what's the point where they're going to notice? So there's a lot of speculation about why it changed over its lifetime the way it did. All right, traces. So this one is a much more recent one. So this happened in, I want to say, December of 2017. So this is the last couple of years. So this one, there's not a lot of information on it because some of it's still coming out. And not a lot of it is public information. There's still a lot of investigation into where did this come from, why is it doing things it did. But the thing that makes this an interesting attack is this is the first attack that directly targeted an SIS. So an SIS is a safety instrumented system. So earlier when I was talking about oil platforms and refining factories and how they have a lot of systems in place to make sure that if something fails, it fails in a safe way. That's your SIS. It's the segmented piece of your system that its entire job is to make sure that if something goes wrong, it doesn't go too wrong. This attack focused specifically on a safety controller. In general, safety systems are isolated and they have their own separate types of controllers. So they'll do things like inverted logic validation. So if any of you guys have done like a digital logic class, you've done some of the math to say if I invert all of these things, it still comes out to the same answer in the end. A lot of these systems will go through, they'll do that, and then they'll compare those to make sure that, yes, I'm actually getting the thing I think I did, it's not doing something funny somewhere along the line. So this was discovered in a, it was not Saudi Aramco, but it was a contractor of theirs doing oil refinery, so somewhere out in the middle of Saudi Arabia. And the reason it was discovered was one of their systems failed unexpectedly and shut off, which is what a safety system is supposed to do. But because it failed and shut off like that, they had to go do an investigation. And as part of that investigation, they found some interesting things that should not have been there. One of which was a Python executable that had been loaded into their network and onto one of their PLCs. So whoever created this, it's still sort of unknown. There's a lot of speculation. A lot of it currently is it's maybe either Russia or Turkey, just because those countries have an interest in controlling oil access to Europe. But what this virus did is it would go in and it then had an instruction to say, go fetch a payload. So it was essentially just a wrapper to get into a device and into specifically a safety system. The reason that it failed was somebody made a programming mistake. So in that code, there is a series of 7 or 8 commands that you can send to the crisis virus. And there are things like update, send system status, send configuration information, go out to the command and control server and update, things like that. One of those commands had a bug in it, which tripped the safety system. So somebody went through the effort of figuring out the system, getting this virus onto the system, and then they sent one of these commands and it locked themselves out. Once this was identified as, hey, this is somebody attacking our safety system, the thing that can potentially kill people if it goes bad, there's a lot of investigation into, okay, how did this get here? What went wrong? Why is it here? Why did it take us so long to notice? And this gets into some of the reasoning behind why industrial control system security is so difficult. So first one is unpatched devices. So I had said, if you have something like a glass factory, you can't turn it off. If you have something like an oil refinery, you can turn it off, but it costs you $500,000 an hour to do so. So you generally don't want to turn it off. And it takes about 3 days to just turn it off and turn it back on. So anything you want to do in the middle there is already several $1 million of lost production. So if you have a system that you can't turn off, you're not going to go and turn it off yourself. And you want it to stay running, so you're not going to get the surprise Windows updates that say, hey, you haven't turned off your computer in a while, we're going to do that for you. So they'll just keep running with software that was potentially designed well before people really thought about security. So I said some of these were made in the 80s. There was not a lot of thought put into computer security in the 80s, especially in embedded systems. Devices in remote mode. So another unique thing about PLCs is most of them have a concept of a mode. And generally it falls into a programming mode and a run mode. And there's sort of a middle state that says this is in a remote configuration mode. So it says I can go to a program mode or a run mode depending on what something on the network tells me to do. If you're designing these systems securely, you put it into run, it's going to keep running along on its own. People can't connect to it and upload your programs. They can't make modifications. It's just going to continue running and doing what you told it to originally. A lot of maintenance technicians really hate that because that means my machine's down, now I need to go and actually flip that switch somewhere. And that somewhere could be down a hall, it could be 50 miles away down an oil pipeline, it could be encased in a block of cement at the bottom of the ocean. It may not be something you can do. So, and it may be something that's extremely difficult to do, where you have to say, okay, now I'm going to run a plane to fly out to the middle of nowhere to go flip a switch. So in general, these devices get left in a remote mode so that people can do maintenance and updates and configuration. And then dismissed alarms. So I talked earlier about that PLCs are really good at generating alarm information, saying, hey, something's wrong here, you should look at that. These specific PLCs that were affected every day would generate an alarm that said, hey, your device is running and it's still in a remote mode. But that was one of several thousand messages that it was generating because of the way it was configured. And so the people working on this facility would say, okay, just dismiss everything. It's kind of like the EULAs that you get when you install software. Nobody actually reads them, you just go, okay, and then you continue on with your life. In this case, it was saying, hey, somebody can break into your stuff. And they went, okay, and continued on with running the plant. But yeah, so that's the Trisis malware. That's the last one of these. Yeah, so things that make ICS security difficult. Again, I talked about the long system lifetimes. So I'm not updating my software. If there's known issues, those don't get updated. A lot of the software wasn't designed with security. The minimal acceptable downtime. So if it cost me $500,000 an hour, in some cases more than that, especially things like oil refining. I know that a lot of automotive plants use $500,000 an hour too as their downtime rate. You really don't want to do that if you really don't have to. And generally security falls into one of those things where people go, I don't have to do that, until it suddenly becomes a much larger issue. Difficult upgrades. A lot of these are custom systems. So it's not like an IT environment where you've got 100 PCs that are administered through some central system, and if you need to push out a policy change or an update, there's tools that do that easily. A lot of industrial systems are a fixed set of components, but they're all configured in different ways. So they may be doing completely different applications that cannot be updated or treated the same way. So if you want to go and you want to do some of these upgrades, you've got to do it on a case-by-case basis. Validation. So this is something that comes in from things like the pharmaceutical industry. If you decide you want to go and make some drugs, the legal kind, you need to get them validated by the FDA, which is a very stringent process where they look at anything and everything in your plant that may potentially touch one of these drugs. And the way that they do that is they say, okay, we looked at your hardware and your software and your programs and your procedures around how you make these things and how you keep track of exactly how much of this chemical you weighed out for this product. We're going to certify that, and now you can't touch anything. If you change even the slightest thing, you're going to have to go through and get audited by us again, and nobody really wants to do that. So if you've got a validated system, once it's put in place, it takes a real major issue to actually go back and update that, because nobody wants to spend 3 months trying to revalidate something that they changed 2 lines of coding. Old protocols. So a lot of systems now, if you hook up a computer to the internet, it's probably using TCP/IP and is using secure protocols, and it might have IPsec or a lot of the good things now that make computers secure. You usually don't want your laptop running telnet because it's not a secure protocol. A lot of these systems use similar really, really old protocols that don't have any security built into them. So there's no data integrity, no validation. Some of them might have like a CRC, but they're not going to have like an HMAC or something stronger that is more of a guarantee on integrity. And unawareness. A lot of people who own these type of systems say, why would somebody attack me? I've got some little factory that makes $100,000 a year in the middle of Ohio. Why would I be a target? And so they'll either say, I don't think that somebody's going to do that, or I don't know that somebody's got the capability to do that. I'm not going to put all of that extra effort and investment into adding security to my systems. So a lot of times the decision between, do I update my plant to make it more efficient, or do I put in the security and keep it running the same way it was with what I see as no benefit? A lot of times it goes away from security. Okay, so that's the presentation. So I'm going to actually start playing with this thing down here now, so we can actually go and talk through how you'd actually program one of these and some of the types of things that you can do to them. All right, so I had said earlier, hold on. There we go. All right, so I said earlier that PLCs are usually programmed on a language that was designed to look like relay logic. So this is what that actually looks like. So there's a few different pieces in here. There's hundreds of different things that you can put in this, but we're really only going to talk about 3 of them today, because they're sort of I guess 4 of them today, because they're sort of the basic building blocks that you can do almost everything with. So the first one here is this symbol here. So it sort of looks like a capacitor type thing. So this is an instruction that is essentially if true. So it looks to say, am I getting an input that's on? If I am, then pass it along to the next thing in this line. So all of ladder logic works along these rungs. And it tries to pass information from this side on the left over here all the way over to the right. The other one is this symbol up here. So it looks the same as the last one, but it's got a slash through the middle. This is the opposite. This is what's called examine if closed. Examine if open. So this is essentially an if false. So if no power is going into the thing that you're looking at, it will say, okay, close the circuit. These little circles down here, this is just an output. So this says, I've got some logic, I've passed through whatever elements are further to the left in my rung. Okay, now I want to send whatever that output is to here. And this little circle says where here is. And the last piece of this we're going to look at today is these things that say TON. So this is a timer that is active while it's on. So you can see on this end there's an EN, so this is enable. So is this timer enabled? Does it have power going to it? There's this DN down here. In the middle you can see it says preset 5000. So this is a number in milliseconds of how long this timer is going to actually count. Once it reaches that 5000, it turns this done bit on. And there are also a few additional hidden ones that aren't used in this, but you can also get information about is it currently counting up. So there's a bit for that, or you can, I believe there's a reset one as well. So this is a very simple ladder logic program. This essentially turns on this traffic light and makes it do traffic light things. So let me actually connect to this. And I guess I'll talk a little bit about what this pile of stuff on the ground actually consists of.
Good, continue.
So all the way on your right, so we have, this is a traffic light. This was a city around here somewhere decided that they wanted to get rid of all of them because it would save them money on electricity. So, and feel free to get up and come up here if you guys can't see from back there. So they decided to get rid of all of these traffic lights. They pulled them all down, replaced them with stop signs, and one of my coworkers went and got one of them somehow. So this is an actual traffic light that was pulled off of a pole somewhere. So next to it, there's all of these wires that run out into this gray box. So that's the actual PLC. Some PLCs have built-in I/O. They're usually a DC or a relay-based I/O. This one is a 24-volt DC I/O. So the two rows over here on the left are inputs, and then these two rows over here are outputs. And if you look in this ladder logic over here, you can see this as local 1.0.data.2. So what that actually means is local, so local to this device. One is just, this is the first device in here. If you've got a system that needs way more I/O than this, there are cards that you can get that slide along the side of this, and actually, I think all the way at the beginning of this presentation, there's a picture of that. Yep. Yeah, so these cards here. So this is the actual PLC, so this is very similar to what that box is. And these cards slide along and actually clip in to, there's a backplane on the side of here that passes all the communications back and forth. So it's got its own internal networking system to handle all of that information. But if we go back to this ladder logic, so 1 means it's there. O is saying this is an output. Data is for that entire bank of output. There is, I think, a 32-bit integer. And it says each bit of that goes to one of those outputs. So if I put in a number, it's going to say, okay, is bit the most significant bit, is that a 0 or a 1? If it's a 0, it's going to turn that off. If it's a 1, it's going to turn it on. And we can take a look at what that actually looks like when it's running in a bit. So that data is that whole 32-bit integer, and then these numbers at the end are which bit of that integer are you actually looking at. And then this darker gray box next to it is just a 24-volt power supply. And then this is connected up through somewhere under this desk is just a switch that's got a subnet on it. So that's sort of all of the components that are making up this system. So let's go ahead and actually download something to it. So you can see here, so here's the path to it. This PLC's got an IP address. Most PLCs have a USB connection, so okay, I just bought one of these, I pull it out of the box, I stick it in my cabinet where it's going to live. How do I actually talk to it? Generally, they'll have a USB cable that you can plug in, and you can use that to do some network configuration. If you look at the bottom of this, there's actually 2 network ports in there. It's for something called DLR, so device level ring. Do any of you guys remember like old ring token networks? It's similar to that, where it'll do bidirectional data transfer. So if you've got a plant that's got a bunch of sensors in it, and you drive your forklift into one of your cables and it cuts it in half, you don't want your whole plant to stop. So it will send it in both directions to make sure that even if you get a single network failure somewhere in that ring, you don't lose the network. So that's why there's 2 ports down there. And each of those can be configured as their own separate network. You can also do some subnetting type things with them as well, but we're not going to get into that today. So yeah, so this device right now just has static IP address. You can see it up here. If we go up to communications, we can say I want to download to this IP address. It knows that this is the device connected to it. It'll ask me, hey, are you really sure you want to do that? It goes through its download. All right, and then it says complete, everything worked correctly. And nothing looks like it's different, except for if you look up in this top here, you can see this green light up here that says controller OK and IO OK. So what this is saying is you're now actually connected to this device. So I can talk to this thing. And I'd mentioned before, there's different modes. There's the remote and the program and the run. So now that I'm connected to that PLC, I can actually go in here and I can change what these modes are. So if I want to go and actually tell it to start running, I can click run, and it will start running along through this program. And you can see as it runs through, these different switches here light up. That basically means they're now energized. So if this is energized and this is energized, basically the signal can pass through here and it gets to this device over here on the end. And as it's running, you can watch here where it says accumulation. You can watch it count up from the timer. All right, any questions so far? Okay. So I'd also said we could take a look at some of these tags. So this value here is the actual, the individual bit data that's being generated from that PLC and then passed to the output. So you can see this here is data, this is this whole big integer, and then each one of these bits, so this one's red, yellow, and green, you can see as they change, the corresponding lights will light up because that output's being enabled. So how does this then get into security? Well, a lot of these devices are out on the network, on either the public internet or maybe behind some not great firewall, or maybe on a local network that you've got access to. After this, I can show you guys just how many of these devices are actually out and about in the world that you can get to. But there's not a lot of security on this right now. There are things you can do to say only accept information from these specific places, or don't expose information that you don't want to. But if you guys want to, if you guys have access to one of these and you want to play with sending it commands and seeing what you can do, there's actually a Python library to do the specific types of communication that are used in PLCs. So if we go over here, so this library is called PyCom. And it has instructions on how to talk to a whole different series of PLCs. So before I run this, I have one other thing I want to explain about how PLCs work. So over here, you can see this folder that says tasks. And it says main task and has this little circular arrow here. There's actually two different ways that you can set up a PLC to run. One of them is in a continuous mode. So essentially, it's got its set of ladder logic. It starts at the top and it goes down to the bottom. And then when it gets to the bottom, it goes back up to the top and it does it again. So it will run through that logic as fast as it can, as many times as it can, and keep doing that until you tell it to stop. That's pretty common in things like manufacturing. So if you've got like a palletizer or a bottling line, something that has discrete countable things, they'll usually be run in a continuous mode where it just runs that program as fast as it can. In process-focused industries, so stuff you can measure rather than count, so that'd be oil, beer, chemicals, all of those type of things. One of the first things that they do when they're setting up a system is they go in, they delete this continuous task, and they replace it with a discrete one. So it says every 5 minutes, run this set of instructions. And a lot of that has to do with the types of processes and some of the physical aspects of them. So if you've got a big physical process, it doesn't react quickly to things. So running your controller as fast as it can doesn't help you at all. So what you want to do is you want to say, okay, here's sort of the interval that I need to check on my system and make updates. And based on that, it will only run at those specific times. So because this is running continuously, probably about 500 times a second, it runs through this entire list of things. But what that means we can do is, if we've got this program here, so all it says it's doing is it says, here's the device, open up a connection to it, and then there's these tags here. Just start writing data to them. And if we go and, which one's the right one? So if we go and we start running this, that is the wrong window. We start running it from this one. It's Python version issue. So essentially what would happen is, I can go through and update this in a minute, but what would happen is all of these lights would start blinking randomly. So what it's going to do is it's going to say, hey, turn on all of these different things. It's going to turn them on immediately, and then as it goes through its next scan, it's going to say, hey, that shouldn't be on, that's bad, I should turn that off. And it will correct it. It's certainly distracting with a traffic light, but if you have something like a CNC machine that's doing accurate control for something, if it suddenly decides it's going to jump off to one side really quickly and then back to where it started, you can potentially cause some damage. Or if you have something like a one of those big generators that we saw from the Aurora test, if you can tell it, hey, change direction real quick and then change back, you can start to do some of those physical damage to equipment, like we saw in that video. So that's true of these continuous programs. If you have one of the discrete ones, well, it's only going to run that code again whenever it gets to whatever that time period is. So if you've told it, hey, this only needs to run once a day, if you sit there and you just continually write information to it, you basically now control that process. You can tell it whatever inputs and outputs you want it to have. So that's why a lot of the security around these is, how do we get these things off the internet? How do we securely network them? How do we get a firewall in place that understands the type of traffic that should be going to these devices? So there's a lot of that sort of controls of the system and the network around these devices. Some of the more modern PLCs can now do things like SSL and TLS, and can do various types of encryption, so you can't just load information out of them or write information to them. One of the things that you can actually do with this one is, if we go back, what's the best way to do this? So if we go in here, we can say, I want to edit this tag right here. So tags are the PLC version of variables. There's this external access field. I can't edit this right now because it's actively running, but this says read-write. This means anybody who can get to that PLC can read it and they can write to it. You can go in and you can turn that off, but that's something that you actually have to do. So there's a lot of making sure that people designing these systems actually know what they're doing and know how to secure them. So a little while ago I'd said that I was going to show you how many of these devices are out on the public internet, and I don't have internet access. Hold on.
That site is blocked.
Is it?
Yeah, 100%. They block everything related to hacking and stuff here.
Okay. Well, at some point when you guys, I guess afterwards, while we're looking at this, I'll see if I can get it through my Works network and actually pull it up. But last I looked, if you search for Allen Bradley, that's the brand name of a lot of the PLCs that Rockwell makes. There's probably about 10,000 of them out there on the internet. If you look for some of the specific ports that are used on the industrial protocols, 2222 is a common one for SIP, and I think 520 is a common one for Modbus, which are both pretty commonly used protocols. There's tens to hundreds of thousands of these devices all over the world that are just publicly exposed on the internet. Some of them are probably honeypots just to see what people do with industrial devices, but there's probably nowhere near that many. So I'm sure at least some of those devices are actual devices you could probably connect to and upload programs from, download programs to, change how they run, potentially read data to them, write data to them. So there's a lot of them out there, and one of the difficulties is making sure people are aware, hey, you've got this thing on the internet that's connected to something that could actually be dangerous. So any questions?
No. Your demo, I think it's because it's on Python 3.8, should maybe Python 3
Yeah.
and then the script.
No, I need to change the path.
Oh, okay, okay.
Let me do that real quick.
It's true. Just to say Python.
Well, you get a specified version.
Yes, Python 2 is on the path, but Python 3 is probably on the system path, so you can probably just know that.
See if you can type Python 3.
Let me just open this back up.
You can just type in C Python 2 and then the Python executable from that directory, and then the name of your scripts, and just run it that way.
Yeah, that's probably the easiest way to do it. What is that? There it is. Oh, where were you?
It's out of like your current directory, so it's backticks and switches.
Yep. I hate typing during presentations.
Oh, I feel you, man. I feel you.
All right, let's.
No worries.
Demos.
Yeah.
The law of demos is that if there's
Yep.
something you can't break, it will break.
Oh yeah.
100%. Oh, there we go.
There we go.
Oh yeah.
Yeah.
Definitely
So
not working normally.
Hmm?
Not working
Yeah.
normally.
yeah. So I mean, this is what six lines of Python, 11 lines of Python, including blank ones, to basically make a traffic light not work the way it's supposed to. And again, this only looks like this because it's using one of those continuous tasks. If it were using one of the discrete ones that says every 20 seconds wake up and change the state, you'd be able to go in and do the movie hacker thing and just change all of your traffic lights to green.
That's crazy.
I don't know about Python.
All right, so that's all I've got. If you guys want to know about sort of other ICS security things, I have plenty of those I can talk about as well. If you guys want to come up and poke around at this and take a look at what's up here, feel free to. And if you have any questions, let me know.
Yeah. Thank you.
Yeah.